by and large, has to do with a fuel-link oxidation. When you go to fuel-rich oxidation, things become somewhat different. Usually, the reactions you have to consider becomes a whole lot more. Taking, for example, methane oxidation, the entire C1 route from the fuel itself to carbon monoxide and ultimately to carbon dioxide, all has one carbon in it. Under fuel-rich condition, you don't have enough molecular oxygen around. Moreover, you don't have enough oxygenated radical species around. That gave rise to a longer lifetime for the methyl radical. Methyl can recombine with itself. It can also recombine with the hydrogen atom back to methane. If it recombines with itself, then it shall form ethane. Okay? So ethane oxidation follows, in principle, the ethylene pathway, with the caveat that ethane, you must abstract the hydrogen from ethane to form ethyl. The carbon-hydrogen bond in ethyl is not very strong. Again, you either react this with molecular oxygen, or you thermally dissociate ethyl radical to form ethylene. What follows is all the same for ethylene oxidation. Okay? That's a small caveat. Now, doesn't matter what fuel you burn, under fuel-rich condition, the most dominant intermediate hydrocarbon in combustion process is acetylene. Acetylene is the most dominant. Thermodynamically, you'll realize that if you take any hydrocarbon, pyrolyze it at a high temperature, below 1,000 Kelvin, the dominant products are methane and solid carbon. Okay? Above 1,000 Kelvin, the dominant products is acetylene and hydrogen. Why? Because of entropy. Dissociation of higher molecular weight hydrocarbon into acetylene also releases quite a bit of molecular hydrogen. The carbon to hydrogen ratio in normal alkene or any alkene species is 1 to 2. Okay? When you get to acetylene, it's a 1 to 1 carbon to hydrogen ratio. So the leftover hydrogen all goes to molecular hydrogen. Molecular hydrogen increase the entropy of the system. Therefore, they are favored. And the entropy effect becomes amplified at a high temperature. Therefore, the switch between methane being the dominant decomposition product to acetylene is dictated by the competition between enthalpy. Methane is a lower enthalpy formation species. So it's favored at a low temperature. When you go to high temperature, entropy dominate. Despite the fact acetylene has a high enthalpy of formation, you will go to that. And that's the fundamental reason why in fuel-rich combustion, acetylene and oxidation of acetylene becomes important. Okay. Acetylene, well, you find this in acetylene torch. And if you burn it, it can undergo very vigorous combustion. Its enthalpy of formation, enthalpy of combustion is very high. And what is the flame speed of acetylene? Well, what is the flame speed of normal alkene under stoichiometric condition, 1 atmospheric pressure? Peter, you stay quiet. 40. So if you take a laminar, premix the flame, well, within a second, it'll probably propagate this much. Hydrogen. How about hydrogen? I'm sorry? Huh? It's about 200 centimeters per second. The reason hydrogen has such a flame speed, partly because of chemistry, but by and large, has to do with thermal diffusivity. That's in the combustion theory side. Next year, you take combustion theory class, you'll learn why. Ethylene has a flame speed about 80 centimeters per second, double that of NLK. The reason why ethylene has a higher flame speed is because its adiabatic flame temperature is higher, owing to the existence of a double unsaturated carbon-carbon bond. When you introduce unsaturated carbon-carbon bond, enthalpy of combustion increase. In the case of acetylene, it's about 120, 130 centimeters per second. Again, largely owing to the higher enthalpy of combustion, therefore higher adiabatic flame temperature, and therefore higher heat release rate. Okay. Acetylene also has other tricks it plays. That's on the kinetic side. Acetylene can react with oxygen atom. And there are probably only a few reactions that's important for acetylene oxidation. You react with the oxygen atom to form the CHCO plus H radical. And that's a chain branching step. You start with O atom producing 2 radicals, or you can form CH2, that's the methane radical, plus CO. Okay? And those are subsequently oxidized very rapidly. I won't want to go into the detailed mechanism. And of course, a now so important path through hydrogen abstraction is to produce the ethynyl radical. Ethynyl radical reacting with molecular oxygen is what gives you the C2 star. Electronically excited C2 species. It has a distinctive emission band known as a Swan band. Now, this emission coming from excited C2 species is green. That's the reason when you look at the fuel-link flame, it's blue because of the CH, electronically excited CH emission. When you go to rich flame, it's green because of an emission from this species. Okay? And in order for C2 star to form, you must produce acetylene first. And that's a fuel-rich chemistry, indicative of fuel-rich chemistry. All right? You won't go down to that bottom if you have enough oxygen around. Alrighty? All right. So other caveat, well, we have beta-acetylation also produce propane, sometimes 1,3-butadiene, and those are miscellaneous pathways that you have to consider, and I won't want to go into detail. Again, it takes about another week to go through all the pathways. I just want to give you the rough idea where you should start looking at this analysis. Yes, Peter?
When you talk about the branching ratio of how these fuels decompose for these simple, smaller molecules, is it governed primarily by the bond association energy?
Yes and no. Qualitatively, yes. Quantitatively, depends on local environment, depends on pressure, depends on a lot of things. Okay. The complexity is such that give rise to the notion that we need to treat this whole thing from the standpoint of detailed reaction mechanism. The empirical rules, there are empirical rules exist. However, the problem is there are too many exceptions. So early days, the argument is that the simplicity is by considering all reactions that you think is going to take place in the system. Okay. Other questions? All right. Let me now take a break and talk a little bit before I talk about pollutant chemistry. Let me give you a historical perspective of this business of reaction mechanism for which this course, summer course, is really based on. Much of what we're doing in combustion chemistry concerns second part of the story. That is, bridge to application between fundamental reaction kinetics with application. You've all heard that the ultimate goal of combustion research is to be able to determine the combustion behavior, combining combustion chemistry with fluid mechanics. All right? ideal goal is you're going to be able to design an engine purely on the basis of computation. At least that's the assumption. Alrighty. Historically, however, chemistry, as you were at the career discussion yesterday, this were fluid mechanics, turbulent flame, combustion chemistry were completely separate for a very, very long time within the combustion research. Okay. On the other hand, this whole thing of a combustion chemistry was started by someone actually is intimately familiar with fluid mechanics. That's Brian Dixon Lewis. This whole thing started from Dixon Lewis. And that happened in the 1960s. He was the one, the existence of Chem-King code and premix code owes to his contribution. Okay? He was the one start writing down a reaction mechanism, start to do computation in one-dimensional laminar flow. As a matter of fact, he put all the initial formulation together. Well, before him was Spalding. I won't go that far. The success of Dixon Lewis, he successfully explained the structure of a laminar hydrogen flame. That was a major step forward. You have to remember, in the 60s, we don't have powerful lasers. It's impossible, it was impossible then to probe the flame structure. Molecular beam mass spectrometry was just the beginning at that time by biology. But we were not able to probe what's going on inside the flame. The success of Dixon Lewis had led to a major boom in combustion chemistry research. Those early generation of people include Eugen Barnatz, Fred Dreyer, Westbrook, well, if I miss a couple of names, jump in. Okay? And there are a lot more others. Cathonay. You all know Philippe de Gaulle, right? He is the advisor of Philippe de Gaulle. Now I'm stuck. There got to be more other names. Oh. Jim Miller. And there are two others I forgot. All right. The reason I wrote out these names, not because anything else. Anyone else you can think of? No, if not. The reason I wanted to write out all of these names is because if you wanted to work in this business, combustion chemistry, I strongly encourage you to go back to those papers and read them. You will learn a lot. One of the things I always say is if you really, really want to be an expert in an area, you need to be technically strong. But you also have to understand the history. Like a sociologist. If you don't understand the human history, you won't be a good sociologist. If you want to be a good scientist or engineer, you won't be very good at it without understanding the history of it. You want to know how this field evolved. You want to see arguments and debates. You want to see how these people, the generation worked on this field, fought against each other. Okay? Science is not only just technical stuff. Science is also about sociology. Now, one of the things you found very useful is go back to, say, 16th Combustion Symposium. You know, this big volume, Combustion Symposium. Now it's called Proceeding of Combustion Institute. One of the things that is unique with this community is going back to the old days, starting from even the first or second symposium volume. You see question and answers at the end of each paper. Now then, the community was smaller. Usually, the way how it happened was that one of those guys asked the other, a critical question in the 16th symposium. And you don't need to do anything else, justify why fuel combustion is important. You just need to come to the next symposium and say, aha, Professor Dreyer, I have an answer for you. Okay? Those question and answer are very useful. And as a matter of fact, they are more useful to understand this research field than reading the paper itself. And I'll tell you my own experience. Okay? And it's also a lot of fun. You get to learn who likes each other and who hates each other. Scientific debate, personal relationship, those are important. And then among you, you will see, 20 years from now, you'll be the leaders of this field. You'll be the leaders of this field. You're going to have friends. You're going to have enemies. Both are needed for advancement of science. Okay? Those are good things. All right? And I'll talk about this actually Thursday. While we're at this topic, let me just jump in and put a footnote on this. Okay? And I want to emphasize this again, that you guys are going to rule this community 20 years from now. Your job is to prove those of us who are talking right now obsolete. Okay? That's the ultimate goal. Alrighty? And this gathering is very important. Not for me, but for you. You'll see that 20 years from now, some of you sitting here will be friends. Some of you sitting here will be enemies. Scientific enemies. Those are a good thing. All right? The other thing is you would wonder, you become a big shot professor? About 20 years ago, I can give you some names, so I won't go into that. The big shots now in combustion community. Those days, we were students too. We go to bars to drink, we get drunk, we carry each other home. Now we're buddies. And then after 20 years, we say, you? So the point here is that you may not see it right now. 20 years from now, you're going to go back and look at your experience right now to be the best. All right? The other thing I want to talk about, the best time of your career is right now. Don't talk about a career. Don't think about a career. If you want something better, there isn't anything better than now. Okay? All right. Going back to that history, you wanted to pick up a couple of these classical papers written by these people before us. Read them, understand them. You form the perspective of what you are working on right now as relative to what they worked on. As the fundamental problems become different. Are we doing better? Presumably, some 30, 40 years later, you want to do something better than them. More importantly, you want to look into the rigor with which they dealt with this problem. Okay, I talked about establishing enemies. You have to remember those days, we were a lot more critical against each other. They were a lot more critical against each other. They ridiculed each other. Okay, that's how science evolved, the fastest. And it's important to have debates. All right. Read those papers, and then what you're working on right now is mostly based on more recent developments. Those are starting necessarily as my prejudice. The GI-MAC effort, you all heard about that, right? That has to do with Michael Frankler, Tom Bauman, at Stanford, Bill Gardiner, now deceased, and David Golden. With other people involved, Ron Hansen, Greg Smith from SRI. Okay. And beyond that, you have Philip de Gaulle, Michael Peeling, okay, till very more recent, Martin Leclerc, and the Milan group. Who has the Milan group? I forgot now. Ranzi. Okay, and so on. You are essentially, I'm sure I missed quite many others. You're essentially taking what they did, expanding. Already. And more recent effort are jet surf and others. Santiago mechanism, to name a few. And of course, Princeton is always in the crossroad of all this development and so on. All right. Now, intellectually, I must say that you learn the most not from this group of work, but from previous generation, where you start to develop something from nothing. And if you have not noticed, all science advancement, the first 90% of the problem is solved using 10% of the time. The remaining 10%, when you want to get a quantitative, it takes 10 times longer. So the foundation was paved back in the 80s. Quantitative aspect started from early 90s or late 80s. Okay. Any questions about this? Any discussion about this? All right, don't write down this list, but I'm pretty sure I missed a lot of names. They're going to get upset at me if I don't mention their names. Huh? Oh, myself, well, I'll leave it out on purpose. Okay. Now, in that process, one of the things I want to caution you is the following. As you pointed out, I was involved in this whole thing starting from the GIMAC effort. I was fortunate to be at the right place at the right time working with Michael Franklin. That wasn't my thesis. I just happened to be involved in it. It turns out that GIMAC grew out from a chapter of my thesis. Then I quit the GIMAC effort and came to Princeton to become a postdoc. Okay. And so that's as far as my contribution. The reason has to do with jet surfing and so on. But that's not important. The important thing I want to say is the following. Fundamentally, our approach, with the exception of the help from quantum chemistry, something I'll talk about tomorrow, reaction rate theory, fundamentally our approach is identical to what Grant, Dixon, Lewis did in the 1960s. Okay? So for almost 50 years, we're doing exactly the same approach. We know a whole lot more about the problem. We learn a whole lot more about in that process. But moving forward, I'm also getting very uncomfortable when an entire research field uses only one approach. Collecting reactions into reaction mechanism, run a chemical code, get results, compare to data, publish paper. You just know a research field is not going to be vibrant if you have only one approach available, one computer code available. You have no competition. Okay? So we'll get back to what I said earlier. You need a friend, you need an enemy. Enemy essentially means that scientifically, I hope many of you will come up with different ways of thinking about this problem. Different approaches, different ideas. And for that reason, I encourage you to go back to these papers by Grant, Dixon, Lewis back in the 60s. I'm sure that if he is alive today, he will look at what we do, what I present in the combustion chemistry course in dismay. The guys still doing the same thing 50 years later. I actually didn't mean, I was just having this curiosity, plugging reaction mechanism into a flame code. I want to see roughly what's happening in the flame. And you guys are still doing the same thing. Okay. At the same time, I encourage you to go to read up some other literature papers, recent development from other fields. One notable example is protein folding kinetics. the complexity of protein folding mechanism and the kinetics is as big as what we deal with in combustion. Okay? They recognized in that community that to write down every reaction step, you are dealing with a losing game to start. So they had to come up with a very intelligent way of dealing with this problem. Okay? Material science, catalysis, they've all went beyond what we are doing. So you must have an urgency to catch up, to come up with your own game. Don't play our game. Our games are too old. Okay? There you have to allow yourself to fail. You come up with 10 ideas, one of them is good. None of them good is equally good, because you challenge your colleagues to think harder. All right? The business as usual is not going to get us very far. That's my personal opinion. You're going to go back, talk to your advisors, and please do. But keep in mind, this is my own opinion. It does not represent what I think the field ought to go. But at the same time, what I really wanted to emphasize here is that I'm going to pose one question to you. Is this field, as far as approach is considered, the only way to get to the solution is to write down every possible reaction you think is going to occur in the system? Are there any better way to deal with it? Okay? Are there better ways to deal with that problem? Now, I want you to also look at this problem from the standpoint of making analogy with other systems. It's a dynamic system, right? You have snow on top of a mountain. That's your reactant, the fuel and oxidizer. Spring comes, snow melt. The water is going to run down. Eventually it goes to the ocean. That's endothermodynamic state, the carbon dioxide in the water. How do you describe this flow system? That's the same problem we deal with in combustion. Your job is to predict the flow rate, or the chemical time, or the flow time, characteristic time involved. Okay? Do you have to map out the shape, the slope, the barriers, and so on of every small creek, every small water channel, before you can describe the overall flow rate of water from top of mountain to the ocean? The way how we are dealing with that problem in combustion, in analogy, is to map out the shape, form, barrier of every small little creek, every detail on this hill. Is that the most intelligent way of doing it? All right, I'll pose that question, and hopefully that one of you will come up with something new. Or many of you come up with different things. All right. Let me get to the part why we learn combustion chemistry to start with. Back in the 70s, nobody took Dixon Lewis seriously. Who cares about chemistry? As a matter of fact, when I went to graduate school in the late 80s, everybody said, why are you studying combustion chemistry? We never need to use it. Why, when you design an engine, then, well, equilibrium assumption is good enough. Fluid mixing is substantially slower than the chemistry. That was the notion then. The major push for combustion chemistry is the recognition of air pollution. Okay? And so I wanted to talk a little bit about that. And this is something I'm sure that all of you guys know. The driving force behind the combustion research, to an extent, a major part of it has to do with air pollutants. This table lists the type of pollutants, source of where they come from, and major effects. Unburned hydrocarbon comes mostly from gasoline engines. Its major effect is photochemical smoke and the greenhouse effect. Carbon monoxide from gasoline engine nitrogen oxides, also from motor vehicles, mostly from causing photochemical smog, and to a smaller extent, acid rain. Sulfur oxides is mostly a problem associated with coal combustion. The source of sulfur is the mineral in the coal structure itself, responsible for acid rain. Then particulate soot remains to be an unsolved combustion problem and impact global climate and causing local problems, skin cancers, and respiratory illness. And down at the end, carbon dioxide, by definition, is also an air pollutant, despite the fact that it is a complete combustion product, causes the greenhouse effect. Okay. We move down fast. Acid rain, I'll jump it through it. Photochemical spark. I live in Los Angeles, and if you live in major metropolitan city and happen to have this phenomenon known as the meteorological inversion, you're going to have to deal with the photochemical smog problem. The car emission, mostly nitrogen oxides, induce a variety of photochemical reactions, leading to a smog. Okay, it's a word of coming initially from smoke and the fog, combining them together, it makes smog. It's just a hazy atmospheric condition. And I wanted to jump through this. I'm pretty sure all of you know the mechanism, but it's not so important. Particulate matter, soot are carbon particles smaller than about a micron, and if you follow a big truck, here in the US, diesel truck, usually you still see a very substantial amount of smoke emission. Okay, that's the stuff you have to worry about. What I really wanted to talk about is the greenhouse effect. You guys all do combustion, right? Many of you, most of you. So that's a touchy subject. So I want to have a brief discussion on this issue. All right? And just briefly review the principle behind the greenhouse effect. We talked about this yesterday. Without atmospheric natural existence of carbon dioxide in the water, this planet would not be inhabitable. The mean global Earth surface temperature would be negative 15 degrees C. Under this condition, ice shall cover the entire planet. Okay? The very reason we are dealing with the temperature quite comfortable is because of the existence of carbon dioxide in the water. The problem is, once you accumulate too much of it, you're going to see a man-induced global warming behavior. The fundamental principle is very simple. The ambient air is mostly transparent to visible sunlight. The sun is more or less a black body emitting radiation most intense by Planck's law at around the yellow wavelength region. Okay? And this sunlight coming into the Earth's atmosphere, some of it gets scattered, but most of it reaching Earth's surface. In the night, the Earth radiates heat back to the space, thus establishing steady state for Earth's surface temperature through infrared radiation in the night. The trouble is carbon dioxide and the water have very wide absorption band in the infrared. Thus, an increase in carbon dioxide concentration would lead to capturing the outgoing radiation. Some facts. Historically, temperature of the Earth fluctuate by as much as 10 degrees Celsius. Okay? And as a matter of fact, most of the time in the bottom part, that's the cooling part of the cycle, and followed by spikes every hundreds of thousands of years. Each and every time this is associated with spike, the increase in temperature is associated with spike in carbon dioxide concentration. All right? The only trouble is that you don't know what is the cause, what is the effect. These two things are coupled. If you increase the Earth's surface temperature, you're going to see more carbon dioxide dissolve from the ocean, reaching Earth's atmosphere, and vice versa. Okay? And each episode of a reduced Earth's surface temperature is by and large corresponding to accumulation of dust due to volcanic activities or due to, a meteorite hitting Earth's surface. At least that's based on the theory. So the correlation between high temperature carbon dioxide are scientific facts. What is also scientific facts are the measurement, which is showing carbon dioxide concentration starting from the time just right around before the Industrial Revolution until today. Unfortunately, I didn't have a chance to update this plot. So carbon dioxide from pre-industrial stage of around 280 ppm now is getting to about 400 ppm, a little less than that. Meanwhile, global Earth surface temperature compared to the main is rising. No, this is CO2. Sorry, this is only CO2. Okay. Other greenhouse gas, methane, nitrous oxide, CFCs are also rising after the Industrial Revolution. Some of this is because of emission from combustion, while others has to do with agricultural activities, notably methane. And the rise in the temperature, global temperature, compared to the last 1,000 years, there's a notable increase in recent years. Okay, so those are the facts. Let's have a discussion about it. And I must necessarily caution you that you all do combustion, so your perspective are going to be very different from street person. It's the street person that influence policy, not you. Okay? I'll allocate about 5 minutes to discuss this. Anyone you want to start? I don't know about Europe. In the States, much of this discussion, you read them from New York Times. Every time I read these articles, it always make me feel very uncomfortable. You have two sides of a debate. It's no longer a scientific debate, it's a political debate. Okay? Usually, you take it extreme, whether science proved it or science hasn't proven it. You're aware of this argument, right? Now, this issue, I apologize, the discussion, this type of discussion, I have not seen this in Europe or elsewhere. I've seen it more in the States. The point here is this. Let me offer my opinion here. Neither side is right. The bigger part of the problem is that if you remember, the goal of science or the utility of science is always disproof. In science, we make a hypothesis, you proceed to disprove it. Okay? And something stays as a law until it's proven wrong. And our job is to prove it wrong. Science cannot prove anything to be right, in principle. So if you say that the science proved beyond a doubt that we're going to see drastic climate change within the next decade, next century, it's hard to tell. But it does not mean that without a science proof, this is not going to be a problem. Okay? All science has established a relationship between one thing and another, thereby raising a risk. You have to deal with it. Let me ask you the other question. You probably are a student, you don't want to own a house. But if you do own a house, you realize your roof is in bad shape. You find a roofer, you say, what's the chance that my roof is going to collapse on me tomorrow? You're going to get an answer between 0 to 100%, right? You say it's 1%, 10% chance the roof is going to collapse on you. I'll tell you what that. If I were your age, I wouldn't care. I'll save the money, go for a Bahamas trip. One day you have children. You say, well, I can't tolerate this 10% chance. I'll cancel my Bahamas trip and I'll fix the roof. This whole issue about debate of global warming and climate change is a risk assessment. And every one of us, each one of us, would have a different risk-taking appetite. But if you stretch things to the limit, this must happen. The roof is going to collapse on me, or the roof is not going to collapse on me tomorrow. A, it's not scientific. B, you never see middle ground to have this discussion. That is the fundamental problem about climate change and global warming debate in this country. Yes, please.
Yeah, but it depends what the risk is. So even a 1% chance of catastrophe happening is still 1% too much. So
I agree. Personally, you ask me beyond this point, if we can agree, the focal point of discussion ought to be an assessment for the risk and the cost for managing this risk. Then we have a common starting point for this discussion. At the end of the day, it costs. So between the risk and the cost, how do you deal with that? Okay. Then it becomes a policy issue. All right. However, without agreeing on that point as a starting point of the discussion, you have no end of discussion. And that's a political argument and discussion in this country went wrong. Okay. I'm very sure in Europe the situation is better. Yes, please.
I was just going to say, I think you give too much credence to the idea that it's an honest debate in the first place.
Mm-hmm.
Because I think, you know, in the 70s and 80s, and even today still, companies that stand to make the most money by keeping, for instance, our major energy infrastructure the same, they're the ones that have the most influence on A, the political debate, but also the media and other presentations of information. So, I mean, for sure in the 70s, 80s, there was concerted efforts by oil companies to put people out that would naysay the data. So I guess at the end, I don't know how much it is an honest debate, you know, where people are really evaluating the risk. I think it's that the people that stand to lose the most money are the ones that have the most power over the, you know, the conversation. And that's the issue.
That be the case. Yeah, it should always be the might is right policy. The people with the money will always win. And in this case, that's what's happening. But I believe that there's a lot of scam out there, especially by the IPCC.
Right, but what did they stand to gain then? Grant money?
That's
I mean, you
true.
think how many rich, global, you know, climate scientists do you see driving the Benzes around?
No, but it's a lot of research money. Too bad. And
So you think that they would spend their entire careers fighting against, you know, trying to do this one thing
Not
and then
really.
it's
I'm
wrong?
saying it's scam on it. The
But to
risk
what
may be
end
there.
though? That's my question.
The risk may be there, but it's still scam on it. It
Well,
may be
why?
there.
You keep saying it, but why? Why is it scary? Why would they?
It's the same reason why I want a certain kind of propellant out there. Because I do research on it.
So what you're saying is that people just pick a thing and then say, well, I've been doing research on this, therefore I'm going to make up this entire conspiracy.
It's not a conspiracy theory, according to me. It's not. It's just that it's overloaded. And
Okay.
the West is really pushing for it because it's been enjoying the energy resources for a long time, and now they want India and China to slow down. That's what they keep saying.
So, okay.
Which, by the way,
So it's not a conspiracy, but the West is trying to
No,
prevent
it's
India from running
no, that's not
it.
that's not the point. The point is that I really hate the fact that every time you read a British newspaper or you read New York Times, they always limit the fact that the Indian and Chinese governments are not doing enough. Well, that should not be the case. You guys have enjoyed it for around 200 years, and as a race, we're never going to agree on this. So they're really pushing forward with the scare moment.
Okay. I'm so confused who they is, though. Scientists? I mean, are you corrupt? Like, are you pushing a research agenda so that you can make your billions of dollars in
It's
research?
not billions of dollars. See, it's not billions of dollars, but I would certainly want my research to be stable.
Okay. So you're counting on individual scientists coming up with this whole kind of collective idea that, oh, there must be global climate change.
There is global climate change. I'm not arguing that.
Okay.
I'm just saying that I really do not believe it's going to be as catastrophic as quickly.
Okay.
That's the point.
Regarding India and China, I want to say something is that the energy we use per day per capita is still much lower than people in Western countries use.
We saw that in the first. We saw that in the first talk.
Yeah.
Per capita.
Yeah. So even you have large population. But for capital, it's still much lower.
Good. Yeah, go ahead.
Yeah, there's no doubt that we have to do a lot of our homework and reduce our carbon footprint a lot, but I think we have to meet in the middle somewhere. And
When was the last time the world met in the middle in anything?
Yeah, that's
Especially on such a touchy issue when your life depends on it, when your way of life depends on it. Especially because a lot of other people are becoming richer, they're getting to spend more money, so obviously they want a better life. And the people in the West have always enjoyed a better life. And back home in India and China, if you tell somebody that we have to cut down emissions and you're going to give up on this, and they're like, why? And that's a valid question. Why do you can never explain it to them.
Right, but isn't the goal to develop technology that allows economic growth without damaging the environment as much as we did?
I agree.
Isn't that what we're all trying to do?
Maybe.
And I think that's
All right. This is a very good debate. Keep doing that evening time after a couple of beer. I'm pretty sure it's fun, exciting. If you're not in the focal point of this debate, and I do not know who is more qualified, the point is you don't have to agree with each other, okay? But having this debate is very healthy. And you are the focal point, and those of you who work for companies, the ultimate decision isn't made by us. It's made by management, but you will have the impact and the influence based on science, okay? And you don't have to agree with each other. And as a matter of fact, as you listen to your conversation, you have more to agree than disagree. Finding a point you agree. If you go to the extreme, say global warming is a hoax, or it must happen with 100% probability with drastic climate change that it can impact our life. If you go to that extreme, then you have no common ground for discussion. You do have a common ground for discussion, so it becomes a quantitative problem. As long as you discuss this in the form of quantitative problem, we can have a viable solution. At the end, you can compromise. Okay? You can't make a compromise between two religions. Yeah, go ahead. But you can compromise anything else. Yes, please.
Scientifically, I also think there is a problem of understanding how many parameters you need to really take into account to come up with a conclusion. Because if you see the graph which I have shown, I could very well say carbon dioxide and the temperature are related by something else and they both grow because of something else. So if I were to see the graph alone, I would come to that conclusion, but there might be more to it. So
there's always more to it. You're absolutely right. There's always more to it. Okay. The argument here is that you don't have to make a decision until you have scientific facts. Well, science, don't give us, in reference to the science we do, don't give ourselves too much credit. All right, that's the point. That is, our job is to prove a notion, a law to be wrong. Okay? Science is based on experiment. In this case, since the only experiment you can do is watch how climate change over time and explain it. In doing so, come up with a bit of wisdom. If you want to do something quantitative, that's become a little bit dangerous. Yeah, go ahead.
What are the theories behind, like hundreds of thousands of years ago, they had spikes in carbon dioxide in the atmosphere? What are the theories behind the increase back then? I know a lot of effort has been put to the increases solely because of combustion, but I mean, there's obviously more to it if the Earth's on a constant cycle like that too.
Yeah. There are several parameters, several factors impact the global surface temperature. First is activity of the sun. The output of solar radiation is not a constant. It fluctuates. It fluctuates over time. Okay. The second factor has to do with amount of dust in the ambient air resulting from volcanic activity or because of meteors. All right. And there are many other factors, including ocean. This is something I don't know very well. The various ocean flows and so on. Okay, there are many factors. All right, the cooling, by and large, is historically correspond to amount of dust that you find in ambient air. All right, Earth's atmosphere was never static. Does that answer your question?
I mean, I'm kind of but like my question was kind of like, what was the cause for the increase in carbon dioxide hundreds of thousands of years ago? A lot of the emphasis being put on that from, the industrial world, and obviously that is increasing it some, but there's also these natural cycles with carbon dioxide.
All right. The carbon cycle goes like that. The major storage of a carbon, there are three. One is in the ocean, as dissolved carbon in the form of, for example, carbonate. Okay. The second is in the rock. The third is in ambient air. Okay. When temperature rises, you're going to see more CO2 dissolved from the ocean. All right? And when you have CO2 dissolved from ocean, temperature rises, you're going to encourage plant growth. Photosynthesis absorbs a large amount of this carbon dioxide. So it is never a runaway cycle. It is a steady state cycle. So whatever we see is a perturbation from that carbon cycle in the three forms. Okay. The issue here has to do with the rate of CO2 emission because of anthropogenic emission of carbon dioxide from burning fossil fuel. All right. That have led to the fact that you disrupt this cycle, steady state cycle, and its balance. All right. Carbon dioxide has a lifetime about 270 years. So once it gets into ambient air, it takes a long while before it disappears. Right. Does that answer your question?
Yeah.
Okay. Yeah.
I just had kind of a higher level comment. So the way that it was described to me by someone more knowledgeable on climate science was basically that they can describe the uptake and the exhaust of CO2 in kind of the global ecosystem with models. But the way that the CO2 in the climate is moving now, the only way to describe the resulting temperature changes is by adding anthropogenic CO2 sources into the model itself. So basically the idea is that without human-generated CO2, you wouldn't see the result that we've got based on the climate models now.
Okay, so I just wanted to instigate this discussion. Obviously, most of the discussion has to happen later. Later meaning the next 10 years, 20 years, as long as your colleagues. All right. Let me now talk a little bit about in combustion. In general, how are nitrogen oxides? We all know how carbon dioxide is produced. We all know how unburned hydrocarbons are produced. Or any intermediates produced in combustion, if you don't complete it, they're going to come out in the tailpipe. There are two things I want to talk about here. One is nitrogen oxides, the other is soot. I don't want to go over all the details, but I give you a feeling of how this thing works. Okay. There are three sources of nitrogen oxides. The most prominent one has been a mechanism proposed by Zeldovich. It's nitrogen oxide thermochemical. Okay. Initially, the mechanism was not proposed to explain nitrogen oxides from combustion. Rather, it was postulated to explain nitrogen oxides formation during reentry at a high temperature. Now, the mechanism goes like that. For the major constituents of the ambient air, you have oxygen. Dissociating into two oxygen atoms, that doesn't happen in combustion. It does happen for reentry, when temperature goes to 3,000 Kelvin and above. Oxygen atoms react with nitrogen N2 to form NO. N atom attack molecular oxygen, generating NO, and continue the chain reaction sequence through the oxygen atom. So it is a straight chain reaction mechanism. Once a radical is produced, the cycle without termination will go on for a long time. Okay. We learned that this morning that oxygen atom is a major free radical species in combustion due to chain branching. So while most of the oxygen atom goes to attack the fuel, some of it will react with molecular nitrogen, producing nitrogen oxides. And that's the thermal NOx mechanism. To complete the story, you also have N atom can react with hydroxyl radical, forming NO. This mechanism is highly sensitive to temperature. So the dominant influence on thermal NO is the temperature. The higher the temperature you go, the greater amount of NO you form, not necessarily thermodynamically, but kinetically. So the way to reduce thermal NOx is by reducing the combustion temperature. Okay, there have been quite many technologies developed for that purpose. The second type of NO is called the phenomenal NO, or the prompt NO. That nitrogen oxide production, this is not a complete mechanism, and what I wrote here is rather old. There have been recent development over the last 10 or 20 years, but I just want to give you a flavor of that. The phenomenal NO has to do with intermediates of hydrocarbon oxidation. Notably, the CH2 radical, the methane radical, and the CH radical. They are both capable of reacting with molecular nitrogen, forming HCN. Okay? And in doing so, it also breaks the nitrogen-nitrogen bond, which is otherwise very strong. And the products of this process, NH, will react with hydrogen atom, forming nitrogen atom. HCN gets oxidized through oxygen atom attack, forming NCO. NCO reacting with hydrogen atom, forming NH, and the result, net result at the end is you have the N atom. The remaining path is similar to the thermal NOx step. Nitrogen atom reacting with hydroxyl or reacting with molecular oxygen to produce NO. In combustion environment, when temperature is high, nitrogen oxide stays in the form of NO. What is emitted from the tailpipe is mostly NO2, nitrogen dioxide. That's come from the conversion of NO in the tailpipe when temperature drops down to around 400 or 500 degrees C. NO now is able to react with oxygen to form NO2. Okay? It is this emission of NO2, by and large, that's responsible for photochemical smog. Alrighty? The other thing I want to talk about, perhaps a little bit more time, is soot formation. All right? And kinetically, the problem of nitrogen oxides formation is by and large solved. There are surprises from time to time, but those are at the tail end of the problem. We are now able to predict nitrogen oxides formation, at least in flames of small hydrocarbons, to fairly good accuracy, within factor of 2. All right? Soot, on the other hand, is a different story. Fundamentally, we still don't have all the answers to the problem. Okay. How many of you work on projects related to soot formation? Okay. What are the topics of your soot study? How to reduce it. Okay. Alrighty. Okay, so jump in if I miss anything. All right. If you look at the soot, you ask what it is. In the microscope, soot is made of mostly carbonaceous particles, and they're aggregates of many small, what we call nearly spherical primary particles. Okay? Interesting enough, it doesn't matter where you make this material, in a diesel engine, in a candle flame, in a bonfire, in a counterflow flame, if you capture these particles downstream after the combustion is finished, you'll find more or less the same structure. Namely, they are aggregates. They are carbonaceous. The mass density of this material is around 1.8 gram per cc. Compared to graphite, it's 2.2. So it's not fully graphitized, but it is mostly graphitic like carbon. Okay. You look at the details of this particle, even though they're made of aggregates, and doesn't matter where it's produced, this primary particle all have diameters ranging from 20 to 50 nanometer, magically. Okay? They're all about 20 to 50 nanometer in diameter. Alrighty? And thermodynamically, the formation of carbon in any combustion process is entropy. So the way to understand this problem is actually from thermodynamic standpoint. The production of soot, in fact, mostly has to do with hydrogen. Less has to do with carbon itself. By forming soot in a field-rich condition, hydrogen get released. This process from, I take an example from propane, producing 3 solid carbon atoms and 4 moles of hydrogen per mole of propane, leads to very large increase in entropy. So it's the conspiracy of hydrogen that left behind the mess we have to deal with, thermodynamically. Kinetically, the formation of a carbon is kinetic. The amount of carbon formed at the end in the combustion process is not determined by thermodynamics, even though thermodynamics gives you the driving force. Kinetically, the dehydrogenation process and the molecular weight growth, polymerization process are highly kinetic. Okay. The mechanism that is available now explains how soot form in the context of a laminar premixed flame. And this is an illustration of a burner stabilized flame. All right? Because it's one-dimensional, it helps us to explain the processes from the beginning to the end. So to explain it roughly, you have a burner. In this type of flame, you have a fuel oxidizer premixed, issued through a porous plug material. You get a flat velocity profile coming out, so you establish a flat flame. If the diameter to the height of the flame, the ratio of the diameter to the height of the flame is large, then this is a pseudo one-dimensional flame. You can neglect much of the radial transport, focusing only along the axis of the flame. We know that visually, you have a blue flame sitting on top of the porous plug. After the blue flame, or rather green in this case, there is a dark region, roughly around 1 millimeter or less in height. After that, you see yellow luminosity. The appearance of a yellow luminosity has to do with soot production. Okay? And the reason why it's a yellow, again, has to do with the fact that the material produced in a condensed phase is more or less a black body material. It can be approximate as a black body material. At around 2000 Kelvin, again, this emission occurs mostly in the yellow wavelength region. Okay? And if you look at the molecular process, you'll find that in the blue flame, the green flame, where the C2 is produced. Above that, if you probe this flame by molecular beam mass spectrometry or by laser-induced fluorescence, you can infer in one case and directly detect in the other case the existence of polycyclic aromatic hydrocarbons. Those are molecular structure extending from the benzene molecule we just talked about yesterday. Okay? They are polycondensed in that there are 2 forms of aromatic carbon. One can be visualized as 2 aromatic rings connected by an alkyl bond. This is not polycondensed. Polycondensed takes 2 benzene rings and fuse them into each other, forming a naphthalene. If you expand this ring structure, you can get a pyrene. naphthalene is the Mars ball. You all know what the Mars ball in the early days is used for, right? Few bucks. Okay, this is this white pellets we use. 4-member ring is pyrene. 6-member ring, when you get to this structure, is a chlorine. Okay, nucleus of a soot is made of aromatics of the size that has been measured, of mostly being the chlorine. 7 aromatic ring. It ranges, has a wide distribution from 4-member ring to about 7, 8, 10-member ring aromatics. So if you look at this picture, it can be hypothesized very easily that something happened after the flame. And what after flame, you ask, what is an unburned hydrocarbon there? In fuel-rich flame, the necessary condition for soot formation, you have an abundant amount of acetylene. So in the early days, acetylene has been thought to be the major growth species responsible for aromatics formation and the molecular weight growth. We now know that acetylene is just one of them. There have been other species I'll talk about a little later. But let me talk about the global process first. Now, fundamentally, thermodynamically, the problem of aromatics formation from acetylene is well understood. Kinetically, it's not. Then those aromatics presumably will coalesce, stick to each other, forming the first 3-dimensional structure. Aromatics, I call them 2-dimensional because they are planar molecules. All right? Once they stack on top of each other, forming clusters of aromatics, you have the baby soot. We call it incipient soot or nascent soot. The formation of 3-dimensional structure typically is called particle inception. That's a funny word. We don't call it a particle nucleation because we actually don't know what that process is. We throw in a fancy word called inception. It's not a scientific word. I can't really define it for reasons I'll discuss later. Once you have these 3-dimensional clusters, it is hypothesized that these clusters undergo further coalescence process, producing large clusters. Large clusters at one point form spherical particles. And each of this line inside of this structure is an aromatic compound. Okay? For one reason or another, early stage of a coalescence of a particle always leads to complete merge of 2 particles, as if these particles are liquid-like. Sometime later, when these particles get to about 20 to 50 nanometer, in that small range of a size, coalescence or aggregation or coagulation of the 2 particles no longer lead to complete merge of 2 particles into one. Rather, aggregates start to form. That's the global physical processes involved in soot formation. At the same time, we also know that although the size of the particle, primary particle, is determined by particle-particle coagulation, the mass of the particle is determined by surface reaction. Surface reaction involving acetylene and other unburned hydrocarbon species reacting directly with the surface of the soot particle. Okay? So that's the global process image of how soot forms. Soot formation is intimately part of the combustion chemistry for fuel-rich combustion. And when you have non-premixed combustion, spray combustion, soot form inevitably. Formation of a soot will impact heat transfer characteristics, will perturb the entire combustion chemical process and the kinetics. Owing to radiative heat loss, your temperature has to drop. And in diesel engine, as a matter of fact, a lot of carbon goes to soot first before it's oxidized. And what comes out also from the engine tailpipe, as far as the carbon is concerned, it's the result of formation of soot and oxidation of soot by as much as 95%. What's remaining is the product of this oxidation process. Okay. So that remains from combustion chemistry standpoint an unsolved problem. So let me discuss why this is a difficult problem. We talked about earlier the production of acetylene in the fuel-rich for fuel-rich combustion, and the driving force for acetylene production is A, high temperature, B, not enough oxygen around. Okay. The second effect surrounding soot formation is you can't form soot without having a flame, as far as gas phase combustion is concerned. So you must have the temperature, must be high enough. You must also have hydrogen atom around, because in order for you to have a flame, you must have hydrogen atom. Now you have three ingredients: hydrogen atom, acetylene, and a temperature. So if you were to postulate the first working mechanism of how aromatics form, which will eventually lead to soot formation, if you knit these three things together, there's the Hawker mechanism: hydrogen abstraction, acetylene addition. Okay. Taking, for example, acetylene as the model hydrocarbon, as the growth unit of aromatics and soot. You start with hydrogen atom, adding to it, you produce the vinyl radical. Vinyl can add another acetylene, form a C4 compound. And C4 compound, you take this hydrogen away by hydrogen abstraction. You form a radical here. Now acetylene can come to add. You add acetylene here, cyclize on both ends, you form the phenyl radical. Okay? Phenyl radical produce benzene. By recombining it with hydrogen atom, the reverse, you can abstract one of the 6 hydrogen atoms to regenerate the phenyl radical. Add another acetylene, loosen the hydrogen, you form the ethinyl benzene. Ethinyl benzene, abstracting the hydrogen atom. Over here, you now can add acetylene. So it's a polymerization process catalyzed by the existence of by the hydrogen atom. This is a simple mechanism of aromatics growth. Now, the trouble is that after this mechanism was postulated, there have been many challenges about the validity of this mechanism. Today, it is understood that this mechanism is just one of the paths to molecular weight growth. The other contributions come from something called a resonantly stabilized radical. Okay? For example, the propagyl radical. Again, let me now give you a rule of thumb for hydrocarbon radicals that can be stable than other free radicals. All right. C3H3 is known as the propagyl radical. Its molecular structure can be written as in this form. You have a triple bond carbon-carbon, triple carbon-carbon bond, followed by a methylene group, whereas the radical site is on the carbon atom. Okay? You can write this differently. You can write this as this to be the double bond, both being the double bond. Therefore, the radical site now is on the other side of carbon. These are two limiting structures. Whenever you have a radical species, you can write logically, based on organic chemistry, two equivalent structures without having to rearrange carbon-hydrogen bond or carbon-carbon bond. Then this must be a resonantly stabilized radical. Why? Nature looks at this thing and said, I do not have to do this, nor I have to do that. I can do something in between. I do something in between such that this becomes half radical on both and the carbon atom. Resonance stabilization basically says that what I will do is I form a half triple bond on the first two carbon atom, then I form a half double bond on the second one. The result is that at the end you have 1/2 of a radical, and you also have on the other side 1/2 of a radical. In other words, this unpaired electron somewhere is shared by all three carbon atoms. In that way, you reduce the tendency for this unpaired electron to react with something else. The result is a thermodynamically and a kinetically stable radical. Okay? Propargyl is one of them. The other example is the benzyl radical, even more pronounced resonance stabilized radical. That is, you have a methylene group bounded to an aromatic ring. Now this radical is shared by all 7 carbon atoms due to pi electron conjugation. The result is a molecule that is ultra stable, and it can exist for a very long lifetime. And if it exists for a very long lifetime, it's also a radical country because it has the capability to recombine with other radicals. Okay? And that's the fundamental mechanism to kill radicals for raising the octane number. That's what aromatics are used for, by this principle. In the case of a soot formation, now because of the existence of a large amount of this propargyl radical, C3H3, once you accumulate enough of them, they shall recombine with each other. In the process, 3 carbon coming in, what you form in several sequential steps to form phenyl radical or benzene in one step. So roughly to sum up this whole thing, the formation of aromatics do have many pathways. The backbone of this whole thing is the Haga mechanism, hydrogen abstraction, acetylene addition. But depending on the field you use, the local temperature pressure environment, the stoichiometry, there can be many pathways. Known pathways, there are at least 24 of them, responsible for aromatics production and growth. Okay. Thermodynamically, the growth process all go into polycondensed pH, with pyrene being the major bus stop. The next bus stop is chlorine. They're both thermodynamically stable, and they also have the tendency to form in fuel-rich combustion. Now, I only have about a minute left. Then you ask, what is the origin or source of propargyl in fuel-rich flames? Well, that source, by and large, comes from the reaction of methylene, CH2, with acetylene. Other source of propargyl can come directly from propene through sequential hydrogen abstraction to form the allyl, C3H5, to propane and arlene, followed by another hydrogen abstraction to form propargyl. Okay. Then once you have that, this is resonance stabilization. The part we still don't know very well is once you have an aromatics of the size of pyrene or larger, how do they come about to coalesce onto each other? Okay? Thermodynamically, the paradox is this. You take a chlorine. Chlorine has a sublimation temperature around 800 degrees Kelvin. So if you take a piece of a chlorine bulk, condense the phase, throw it into the flame, the first thing it will do, it will evaporate. Okay? Flame temperature typically is above 1400 Kelvin. Yet, if you capture soot, large or small, from the flame, break it apart. You break it apart carefully so you do not break an aromatic ring. You measure its mass. Well, that mass is about the size of a chlorine. That remains to be an unsolved scientific problem till today. So all the soot models out there all assume that the first soot particle comes from coalescence of a pair of pyrene. In other cases, a pair of naphthalene, a pair of chlorine. That has no fundamental basis for us to do that. It's just because we don't know it any better. We're violating the second law of thermodynamics. That's something I'll talk about on Friday. Okay? So, all right, I want to end today's lecture here, and I want to caution you the 2 points I made today. The unsolved, or major unsolved combustion chemistry problem. Okay? Professor Bill Green just walked in the middle, and if you don't know him, he is the pioneer in doing automatic mechanism generation code. That is, beyond what we've done early days, you're putting reaction one by one, typing it into a file. He's developing the rules you need to generate these reaction mechanisms based on what we know. Okay? So we're moving forward. This is one direction to go. Must be an important direction to go. And I hope 20 years from now, you will not do what we did, writing reaction one by one. But there's tremendous of a science you can do. How do you make this really truly automated? And there are many rules we need to develop. How do you develop these rules? Okay. The second problem I want to emphasize, give me 30 seconds, is the problem of soot formation as far as combustion chemistry is concerned. It's still an unsolved problem. Okay? That not only has to do with the mechanism of aromatics formation in flame, but also has to do with the fact that we still do not know how to explain from first principle the formation of first particle from gas phase species in the flame. All right? All right, this is a group photo time, and we'll stop here. Thank you.